Welcome to the flock. Let's dive into the principle of Le Chatelier and shifting directionality or equilibrium, and how we can use that to write KEQ or KC equilibrium constant expressions. Stick around to see how it's done. First, we need to understand what the heck Le Chatelier's principle even is. Basically, the premise of it is that if you have a chemical reaction and you do something to that chemical reaction at equilibrium, the entire reaction system is going to try its best to undo whatever you just did to it. So in other words, chemical reactions are literally just toddlers, because toddlers' whole goal in life is to literally undo everything you just did.
How can we trust him?
Come on, he's just a baby.
Notice that I specified the chemical reactions for species that are either gases or aqueous state. The other thing we need to keep in mind is that Le Chatelier's principle is not applying to solids or liquids in a chemical reaction. We're only going to be looking at chemical species that are either in their gas state or an aqueous state to affect equilibrium. So let's say we were to increase the concentration of A. If we increase the concentration of A, we have now done something to the chemical reaction that it wants to undo. The chemical reaction is going to want to decrease the concentration of A. And the only way you can do that is by shifting more to the products, because then it converts more of A into C and D, thereby decreasing the concentration of A. What if we decrease the concentration of A? Well, the system is going to want to undo what we just did to it. It's going to want to increase the concentration of A. So the reaction is going to shift more towards the reactants in order to convert D and C back into A and increase its concentration again. How about B? What if we increase the concentration of B? Well, in this case, it would have no effect because B again is in its solid state, so it will do nothing to the shifting of the equilibrium. What about C? What if we decrease the concentration of C present? Again, this will have no effect because C is in a liquid state, and that does not contribute to the equilibrium expression. However, if we look over at D, we notice it's in its gas state. So we could say, hey, what's going to happen if we increase the concentration of D? The entire reaction is going to now try and decrease the concentration of D. Its goal in life is to undo everything you just did. And the only way it's going to decrease D is by shifting the entire reaction back to the reactants in order to convert D and C back into A and B. Likewise, if we decrease the concentration of D, the reaction is going to now want to increase the concentration of D. And since it wants to increase it, we're going to have to shift more from the reactants back to the products, making A and B react together to create more D and increase the concentration again. So let's try this way of thinking, this concept, on an actual chemical reaction. We have hydrogen gas reacting with nitrogen gas to form ammonia gas. Notice that this equation has equilibrium arrows, so we know that it is at equilibrium. We also note that all of these species are in their gas form, so they all can affect which way the equation will shift. In this case, the question is asking us what will make the reaction shift to the left. So we want to think, okay, what is going to cause this reaction to go back to the reactants, to go to the left side of the chemical equation? Let's try a few things. If we increase the concentration of H2, and notice that I'm using these brackets every time. These brackets mean concentration. So if you ever see brackets anywhere, just know that it is the shorthand for concentration. So let's increase the H2. If we increase the concentration of H2 gas, the system wants to undo what we just did, so it's going to want to decrease the concentration of H2 gas. In order to decrease it, we're going to shift over to make more products. So that's not shifting to the left. That would be helping it shift to the right. So hopefully you recognize if that's going to help it shift to the right, what if we were to decrease the H2 gas instead? Well, if we decrease, the system is going to want to increase H2 gas again, and so it's going to shift over to the left. All right, so we've got one thing that would make this chemical reaction shift to the left, but there's other things we can do to it too. Let's take a look at the nitrogen gas. What if we increase the nitrogen gas just like we did before with the H2 gas? When we increase the nitrogen gas, the system will want to undo it and decrease the nitrogen gas present. So it's going to shift more to the product side to decrease the nitrogen gas present and make ammonia. Not what we want. But since we know that increasing it will cause it to shift to the right, we know that decreasing it should have the opposite effect. The system will want to increase N2 gas now and force the reaction to shift back to the left to increase the N2 gas present. So a second thing we could do to shift the reaction to the left is decrease the nitrogen gas. Now, what if we added a catalyst to this reaction to lower the EA hump and speed it up? Would that make it shift to more products, more reactants, or what? Well, yes. The answer is yes. It would help it shift to more products and then more reactants again. So adding a catalyst that's not getting used up in the chemical equation, because that's what catalysts do, they just speed it up but aren't used up, would have no effect on the chemical equilibrium. So that's not one of our options to help shift it either direction. Let's try manipulating our last species. What if we were to decrease the concentration of ammonia present? Well, if we decrease it, the system is going to want to undo what we just did to it and increase the ammonia. In order to increase ammonia, the reaction has to shift more towards the products to make more ammonia. So that option's kind of a dud. However, if we were still looking for ways to shift it to the left, if decreasing ammonia causes to shift it to the right, then increasing ammonia should cause the reaction to shift back to the reactant side. And in fact, it would. If you were to pump in extra ammonia into this reaction, say in a sealed vessel, it would end up forcing it back to the reactant side. So a third thing you could do would be increasing the concentration of ammonia present. Now that you've seen me apply this rationale, go ahead and pause the video here and see if you can apply the same rationale to have this chemical reaction shift to the left. Make sure that you select all that apply from the list below. Ready? Go! Let's see if you got the answers right. Remember, just as we said before, the catalyst is going to speed it up in both directions, so essentially it does nothing in terms of shifting the equilibrium. Alright, hopefully you got B and C as your two answers that would help this reaction shift to the left, back to the reactants. Now that we've seen and applied the logic for trying to figure out if an equation will go to the left or to the right, let's see if you can figure out what from the list below would cause this equation to now go to the right instead. Go ahead and pause the video now and make sure you select all that apply. Let's see if you picked the right answer choices. So to make this reaction shift to the right, we can pick both A and E as options that would do so. Now let's talk about the chemical equilibrium aspect here. We represent chemical equilibrium as KEQ or KC or sometimes just K. In all cases, you're going to see an uppercase K to represent chemical equilibrium, but you'll also be seeing a lot of lowercase k's to represent rates. So chemical equilibrium should be thought of in terms of rates, i.e. how fast is A going to B and how fast is B going to A. Now at equilibrium, that's when the rates are equal to each other of A going to B and the rate of B going back to A. This is most commonly represented as the rate forward, or F subscript, is equal to the rate reverse, or R subscript. So the rate of A turning into B going forward is the same as the rate going reverse of B going back to A. At this point, the concentrations of A and B are not changing. They don't have to be the same value, so it's not like both A and B are 2 molar, for example. That's not what's happening here. It's that their rates are equal to each other and the concentrations are not changing when those rates are equal. I know that that's a little bit of a difficult concept to wrap your head around, so here is a little bit of a silly analogy to represent this. Let's say that pond A is our A from the previous chemical reaction, and pond B is our B from the previous chemical reaction example. We know that to go from pond A to pond B, we've got 2 ducks waddling their way on over per hour. And to go back from pond B to pond A, we also have 2 duckies waddling their way on over per hour. So their rates are the same. However, let's take a look at the concentration of duckies. In pond B, we have 4 duckies, and in pond A, we have 8 duckies. So the concentration of duckies is 8 in pond A and 4 in pond B. The concentrations don't match. The rate of the duckies going back and forth does. There's 2 ducks per hour. And if 2 ducks leave pond B and go to pond A, and 2 ducks leave pond A and go to pond B every single hour, the concentration will remain the same. We're still going to always have 4 duckies over here every hour, and 8 duckies over here every hour. Albeit not the same exact duck, but let's just assume they were all clones of each other, I guess? Now here's something else you should know. The lowercase k is what we represent as rate. The rate forward is represented by a lowercase k subscript 1, just to indicate that it's the rate that's going forward. And the rate reverse is a lowercase k with a -1 subscript, just to indicate that it's going backwards. I like to represent the rate k as a cursive lowercase k. This makes it really easy to distinguish between the uppercase K for KEQ or KC or just K by itself. I highly recommend that you do the same because when you're doing these calculations quickly, like say on an exam, it might be easy to confuse the uppercase Ks with a lowercase k. If you have the cursive though, you should be set. If we graph equilibrium, or KEQ, it's easier for us to figure out how we get the KEQ mathematical expression. So let's go ahead and plot the graph so that you can see where the expression actually comes from and why. On the y-axis, we have our rate, which is our K, lowercase, and on the x-axis, we have time. Initially, when our reaction starts, we have no B and we have all A. So it's going to start high, at least initially, and then slope downwards until it gets to a very flat part where it won't be changing its rate any longer. And as we just mentioned, when the reaction first begins, there is no B present. So we're going to put the initial starting point for B at 0. But as A gets converted into B, the rate for B formation is going to increase substantially and then also reach a flat line. The point at which both of these chemical reaction rates become flat is where our equilibrium is. Now, the important takeaway from putting this on graph form is that this sloping down and sloping up of our A and B chemical reaction species sort of looks like the exponential function of y equals a times b to the x power. So keeping our y equals a times b to the x power format in mind, we can also think about the fact that KEQ or KC, chemical equilibrium, is literally all about the rates, as we just mentioned before. So KEQ is literally defined by the rate going forward being equal to the rate going to reverse. Since we know that's literally the definition of equilibrium, we can further break apart the rate going forward and the rate going reverse to fit into a mathematical expression. The rate going forward is equal to our lowercase k, which I like to represent by the cursive lowercase k, base 1, meaning it's going forward, times the concentration of A, as we just saw in the graph. Remember, this looks similar to K1 times concentration of A, just like our exponential function. Likewise, if we break apart the rate reverse and set that equal to its counterpart of the cursive lowercase k -1, the reverse B to A, and multiply that by the concentration of B, we can see that that looks awfully similar to A times concentration of B raised to some x power. So then what we can say is, okay, well, if KEQ is equal to this whole expression and each individual expression is equal to that, then we can just set these parts of the equation equal to each other. K1 times the concentration of A is equal to K-1 times the concentration of B. Now in math, we want similar terms to be on the same side. So if we further manipulate this and divide each side by K-1, we then see our mathematical expression look like this. K1 over K-1 times A is equal to the concentration of B. We still need to get the concentrations on the same side, just for mathematical sake here. So we're going to divide off the A from both sides. And what we end up with is a new expression where the rate going forward divided by the rate of reverse is equal to the concentration of the products, because that's what B represents, divided by the concentration of the reactants, because that's what A represents. And since all of this, if we go back through, all still represents KEQ, we can then say that the KEQ expression is equal to the rate forward divided by the rate reverse, or KEQ is equal to the concentration of the products divided by the concentration of the reactants. See why it's so important to have a lowercase cursive k to represent the rate versus KEQ capital K? Now, the only thing we don't want to leave out here is this little x that we determined from our exponential function graph. That little x is up here in the corner, and that's going to be the mole value tied with the chemicals in the balanced equation. In other words, you're going to have to write a balanced equation and use the coefficients from the balanced equation as exponents in your KEQ mathematical setup. Let me show you what I mean by that with an actual problem. If we were going to write the KEQ equilibrium expression for the following chemical reaction, we would need to put the products over the reactants, as we saw before, the concentration of B over the concentration of A for our KEQ. Notice that in this expression, we have different mole value coefficients, and those different coefficients are going to end up as our exponents in the expression. If we were going to write the KEQ expression for this chemical equation, we have one product that we put in the numerator for our B. So we're going to write NH3 in brackets to symbolize concentration of ammonia, and we're going to take this 2 and put it as our exponent in the upper right-hand corner. Now, the only reason I can include ammonia in this expression is because it's a gas. Remember that if a chemical is a solid or a liquid, we do not include it in the KEQ expression. Next, we need to focus on our reactants. That's going to be in our denominator. We have H2 gas, so let's put H2 in brackets, and we see that it has a mole coefficient of 3. That 3 is going to go in our exponent in our equation. The next reactant we have is nitrogen gas. So we're going to put nitrogen gas down here in the denominator as well, and we're going to give it an exponent of 1. Again, we can do this because both of them are gases and not solids or liquids. So that is our final KEQ expression. Now that you've seen me try it, go ahead and pause the video here and see if you can set up the KEQ expression for this chemical equation. Ready? Go. Let's check your math. And your final KEQ expression should look like that. If you got that right, give yourself a nice big pat on the back. Make sure you test yourself on these concepts before you move on how to use KEQ to calculate. Make sure that you can answer what will happen if O2 is removed from the following reaction, and what the KEQ or Kc or K equilibrium expression is for the following chemical reaction. If you'd like to check your answers, go ahead and comment below and I'll be sure to let you know. In this video, we discussed how Le Chatelier's principle is essentially just demonstrating that chemical reactions are toddlers because they're going to undo anything that you do to them when they're at equilibrium. We then discussed how the chemical equilibrium is represented by an uppercase K, and that could be just K, K base C, or K EQ in the base. And it all has to do with the rates. The rate going forward being equal to the rate going to the reverse. And those rates are represented by a lowercase k, which I like to use cursive for to make it really distinctive. We could then use the fact that the rate going forward being represented by lowercase k base 1 being equal to the rate going in the reverse, or B to A, represented by k lowercase base -1, setting all that equal to each other because that's all equal to KEQ, then gives us the ability to graph and see that it follows a mathematical equation similar to an exponential function, where we can say that KEQ is actually equal to the rate going forward divided by the rate going reverse. Or KEQ is also equal to the concentration of products raised to the mole coefficient value from the balanced chemical equation divided by the concentration of reactants also raised to their respective mole coefficient values. And that gives us the ability to set up equilibrium expressions, to later use them to calculate. That part's in the next video though. Please give this video a quacks up, and when you're out of luck in chemistry, subscribe to the duck. Stay quacky, my friends.
No ducks, no glory.